Origami traces its origins to Japan in the 7th century, not long after paper was introduced to the country. Photonic origami, on the other hand, traces its origins to the 21st century in Israel. To be more specific, the technology debuted in Optica just last month. Like traditional origami, the technique can create incredibly intricate objects using precise folds. The technique utilizes lasers to create highly transparent, ultra smooth 3D microphotonic devices with nanometer precision. The possibilities for the technology are broad, holding implications for astronomical research and for the development of high performance integrated optical devices. In today's episode of All Things Photonics, we speak with Tal Carmon, a professor at Tel Aviv University who led the team behind the research. That conversation is up next.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more. Today's episode is also brought to you by American Elements, the world's leading manufacturer of engineered and advanced materials, with a catalog of over 35,000 products available in both industrial bulk and laboratory quantities. To learn more, visit AmericanElements.com. American Elements. Now invent.
From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics. Tal, can you give us a very brief overview of this research work?
So this research work is about a very thin layer of highly transparent glass on a silicon chip. And until now, you could do only two-dimensional planar photonics with it, resonators, waveguides, and so on. But when you wanted to go 3D, you couldn't, just because you relied on lithography. So you can make one layer and another layer and so on, but you couldn't fold it to 3D. And the thing that we did is, well, I have here this paper here, just like we all know, and you can cut any shape out of it, and then you can fold it to get 3D. So what we did is actually going on chip, flat surface of glass, can be only 1 micron thick, which is 1/100th of the thickness of your hair, and we can fold it to any angle that is needed and create three-dimensional structures.
Now, what inspired this work, or what led to it?
So I'm doing on-chip resonators from 2020 for a few decades, and everything is planar. And one day, my student came to me. We had to align a CO2 laser, which is in the infrared. And the student, Mania, she told me, look, I cannot see the spot where the laser hit, and the camera also cannot see it. So I told her, look, quite simple. Increase the power until it will be heated to, let's say, 500 degrees centigrade. And then, just like we know from warm things that start glowing, black body radiation, it will start glowing, and you know the place where the laser hit the glass. And she came to me after a while and said, look, it's not working because the glass folds exactly at the place where the laser hit. So this folding, this origami, was discovered by accident. What happens there, the mechanism is such, it's very similar to there are planets where humidity is making one side wet, folding to release seeds. And the mechanism here is quite similar. The glass is heated from one side, so this side turns liquid. And liquid have surface tension. They try to make it from flat surface into a droplet, so it try to pull things. On the other hand, on the other side, the glass is not liquid, but it's also not solid. We call it glass temperature. When you reach the glass temperature, it becomes viscous like honey. So one side is letting it fall, and one side, the upper side, is pulling it to fold, and it's fold. And we can control this process. We can stop at any angle you want, 37 degree, 0.5. Okay, we will give small pulses until we'll reach this angle and stop. So this is the process.
Now, when we hear the word origami, we think of these very beautiful, delicate paper sculptures made through folding.
Yeah.
So I guess, in the spirit of origami, how much creative control do we have over these structures? And would we describe them as delicate or more robust, I guess?
So it's robust. First of all, this glass is very rigid. The rigidity is comparable to steel. And one thing this is an excellent question. We were wondering whether we can fold things in several knees. We were afraid that the folding bar will hide the spot where the laser should hit and don't let it hit and fold the glass. We were surprised though that because the beam is focused in a conical manner, even if there is an obstacle somewhere in between the focus and the lens that focus the light, still light pass through other ways and reach this focal point. So we can make needs even if part of the field of view of the laser seems to be hidden. We might have to increase the power a little bit to compensate for this partial hiding, but we can fold in several needs. We can make helices, like fold a straight bar into a helix. And we can stop anywhere we want. So we can give me a desired structure, and I think we can do it.
Now I'm curious, what are the practical applications for this technology? What do you expect we'll be using it for in the future?
So one thing is that, like, what are the application of 3D printers? I mean, you could print things in 2D, cut things in 2D, and I mean, the imagination is the limit. That said, one thing that we can do, first of all, there are three-dimensional printer now that print glass, including with like micron resolution and so on. The thing is that the glass that is printed nowadays is not transparent, not highly transparent. For example, the silica that we are using is grown on silicon, so we take very pure silicon, like the one that you make computer chips from, and you put it in a clean oxygen environment while heating it. So, like rust growing on iron, there is a glass silicon oxide layer that is grown there, and it's very pure. Light can propagate for 1 kilometer in this glass. Limited by the roughness, by the way, not by the transparency. The roughness scatter a little bit of light, even though it's nanosmooth. So we can propagate 1 kilometer, which means that if we are building a resonator, this resonator will function as a sensitive sensor. If we are building a laser, this laser will have a low threshold and high coherency. High coherency means that we can measure things more accurately. And this 1 kilometer propagation is in comparison to 1 centimeter with three-dimensional printers. So if you want to just build a mirror with a printer or some structure that will tilt the light, that's fine. But if you want to build high quality photonic structures, then we can do it with our technique. So we can take this resonators that we build, concave mirrors, micro lenses, and build three-dimensional circuits with them. One thing that is most attractive, I think, is the fact that we can make very large structures that are very, very light. Their weight is very, very small. And actually, we get here to the ultimate limit because if we just make the leg of whatever we do, if we just make the cantilever beam that we make thinner, then it will just fall down by gravity. So we can make few millimeter structures, even 1 centimeter structure, that is only 1 micron thick and fold it into a structure. Now, one thing that is attractive is levitation. Currently, optical levitation that was shown by Ashkin during the 70s is limited to a micron scale structures. It's very attractive to levitate something large because it's like frictionless. You can do it in vacuum. Unlike acoustical levitation, for example, you can do it only in air, and there you have the air friction or viscosity. Superconductors, you should cool them down. They are sensitive to magnetic field. Electrostatic trapping tweezers, they are operating not direct current. They are like alternating current. So they and optical tweezers is the only one that is like frictionless, not sensitive to magnetic field, but it's limited in the size. So one idea is to build a structure that is a mirror and has some legs and other things, and let light multiply reflected between this mirror and another mirror, let's say 1,000 times, so that we can resonantly enhance the power of levitation and levitate large structure. Also, light sails for outer space. We can make structures that have some 3D things that will help these light cells, and also a very thin layer of glass. So I think in the immediate range, levitation of large objects, which are needed for sensitive measurements of forces, then it can help light sails, and then anything that you can imagine. You can put two mirrors, one in front of the other. Previously, this mirror were flat, planar, and then you fold them and let light multiply reflected between this mirror. It apply radiation pressure. We were reporting on this effect long time ago in 2005, and it can like vibrate because of radiation pressure, and it can be an optomechanical device. So these are the few things that I think. But any of the listeners is more than we will be glad to hear any idea of what you can do with photonic origami for optics or for anything else. But we should remember that the thing can be smaller than the diameter of a human hair, the whole thing.
What would you say are the next steps for this research? Are there any things that you want to focus on sort of immediately, or?
So the levitating mirror, I think, is highly attractive. Yeah, just because no one did it before. There are theoreticians that should suggest that we will be able to measure very weak forces with this levitating mirror. One force that is in particularly interesting is gravity, since there is a mystery right now related to astrophysical, astronomical topics, which is like dark matter. We see
Right.
less matter than we measure gravitationally. And one possible solution that theoreticians suggest is that measuring gravity over short distances might show us that Newton was wrong And gravitation doesn't depend like 1 over the distance square, but there is small deviation from this power of 2, like 2 plus some constant, some epsilon, and this can explain the astronomical mystery related to dark matter. It is a long shot. There are many challenges on the way. One of them is that gravity is the weakest force in nature. The other is that we think of a laser as something that's providing a constant power, but fluctuation in the power give rise to noise. But maybe building a levitating cavity mirror, and we should fold it, of course, to have legs, to have its center of gravity below the point where light hits. Maybe we will be able to measure weak forces with that.
I wonder what advantages would that type of system provide over maybe the conventional systems that are used to measure gravity?
Yeah. So when we measure something, we want enhancement of the measurement. And one way of enhancing the measurement is to use resonators. So if you let light go forth and back 1,000 times, the lifetime of the photon inside is longer. I mean, it goes forth and back few centimeters, and this lifetime is related to narrower bandwidth in the frequency domain. We call it the Fourier space. And for this reason, the number of times that light go forth and back in the resonator is called finesse. How fine can we measure? How narrow is the resonance, and how small of a shift we can measure? So in this levitating cavity mirror, we get resonance enhancement of both. One of them is radiation pressure, and this is something new. It was not done for levitating structure in the past. The other is resonantly enhancing the sensitivity of the measurement. So we can also measure the position of this cavity mirror very precisely. So this is the advantage over other methods. Other methods, for example, the oldest measurement is Cavendish experiment. You take one sphere of heavy metal and another. You hang one of them from a wire. You try to pull it to let it rotate. So these are the other ways you can do it. And we are benefiting resonance enhancement mostly of the measurement accuracy.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.